Okay, so false alarm. I got you guys confused with another class. Our test is until next week. It's not this week, so I might have said this test was this week. But it's next week. We have one more full week. We have a quiz Wednesday again. And then the first exam is a week from Wednesday. Not 2 days from now. Next Wednesday, not 2 days from now. Right. Yeah. Yes, I've got number 3 here, and I've already handed back number 1 and number 2, so I still have yours if I didn't give it back to you. All right. So, like I said, normal week, we got homework due Sunday night, and then the quiz for Wednesday will be available at 9 a.m. this morning. Let's see how we did on this homework from last night. Maybe not. Hello. So last night was chapter 5, right? Okay, maybe number 9. Take a look at number 9. It seems to stick out as one that is slightly more difficult than the rest, so let's look at number 9. Unfortunately, I can't make this bigger. I'll just write out stuff that's small. Okay, so it says the following frequency distribution provides certain condition prevalence frequency distribution for 66 regions. So this is like the percent of regions and then the frequency. So it says determine the number of outcomes that constitute the event not C. So C says the event that a prevalence has of at least 5% but less than 10%. At least 5% but less than 10%. So we look at the corresponding ones. So at least, so this says 5 to 6. That right there says at least 5 but less than 10, but then we want the event not C. And they want the number of outcomes. The number of outcomes. So greater than 5 and less than 10 would be all of these. So then not C would be this 8 and this 3. So I think it's 11. Okay, then it says the event A and B. Okay, so we got to remember the difference between and or. And is where both things have to be satisfied. Or it could be one or the other or both. So when you say and, this is where it may get a little tricky, because you may think I'm just going to count up everything in B and everything in A and add them together, but that's not right, because it's got to be A and B would be both have to be satisfied. So what's A? The event that at least 8%, and B says prevalence less than 7%. Okay? So at least 8% and less than 7%. So at least 8 would be all these, and then less than 7% would be these. So how many outcomes are both of those? How many outcomes satisfy both of those? That's what and means. 0, right? There's no outcomes that are both greater than 8 and less than 7. So if you're thinking you're going to add up all those different situations, that's the or situation. That's or, where your event could be A or it could be B. But there's no regions here where both of those are true. That's what and means. Okay? So here's C or D. C or D. So C is at least 5%, but less than 10. At least 5, but less than 10. That's all that. And then D is less than 9. So then less than 9 would be starting here all the way down. So we want it, as long as it gets hit by one or the other or both of those, then we count them. But we don't want to count twice, right? So there's overlap in C or D. We don't want to count that twice. So what are we going to do? We're going to count up everything that got hit by those two events. So it's going to be all that. But these ones that are in both of those, we don't want to count those twice, right? So it's going to be 8 plus 12 is 20, plus 19, 39, 53. I think it's 63 of them. So I just added up all the ones I circled in red. Okay, and then finally, determine the number of regions that constitute C and B. All right, another and. It's got to be both. C and B means it satisfies C and also satisfies B. So what's C? At least 5%, that's C, and B says less than 7%. At least 5, less than 7. So that's those two. So at least 5 would take you all the way up like this. Less than 7 would be all this like this. But now it has to be, now it's and. Now it's and. You got to have both. So I think that's 19 plus 14. No, 12 plus 19. Okay, questions on this one? So all the rest were, you guys did real well. There was just a little bit of trouble with this. I would guess that it's the and gets confusing. When you're saying that the event of one event and another, it's got to be both. The ones that you count up have to meet both criteria. If it only meets one criteria, it doesn't satisfy that condition of and. Okay, questions on that homework? Okay, cool. So we're going on to chapter 6. Okay, chapter 6 is about the normal distribution. We've already kind of touched on this, but we're going to look at it more in depth now. So normally distributed variables. We saw, okay, so what are variables? Variables are things that can take on different values that we take data from. So we could say a variable is the number of siblings that you have, right? We could go around the classroom and get the value of that variable for everyone in this class. 0, 2, 3, 1, 1, 1, 0. So that variable takes on different values. In the case of the one I suggested, it takes on the number of siblings a particular person in the population has. So then when we look at the distribution of all the data of a certain variable, we get different distributions, and this normal is a very common distribution that you get. All right, so before we talk about that, let's talk about shape, distribution shape. So here's some examples we've seen in the past. And this was the relative frequency for a number of TVs in a household. I don't remember what this was for, but this was, I remember, the stem and leaf plot. Here's prices of DVD players. And what we see is that when you graph all of the data, the distribution of the data takes on a shape. So like this one. We look at the frequencies. So what is this? This is values of the variable. Our variable, in this case, number of TVs in your house. So the x-axis is the different values of the variable. And then what's the y-axis? So what's sticking up is like what's the frequency, or how many of that value do we get? So most people have one TV in their house, right? Not most, but the highest frequency is 1, and then next is 2. So then when you look at the tops of these frequencies, you get a shape to the distribution. So we can just imagine the tops of these bars, right? And that gives a shape of the distribution. So these curves that we look at are looking at different values of the variable this way, and then the height of the curve is like the frequency of that value of the variable. If it's higher, then more of the data had that value. If it's lower, then less of the data had that value. Okay? What about this? How do we see a shape of a distribution here? So where are the values of the variable? Going this way? These are the values of the variable, like this? Going across like this? Yeah? Yeah, right, they go up and down. So this we got like 19.9, 20.0, 20.2. So really, these stem and leaf plots are kind of turned 90 degrees. So if you turn them this way, then you can see it, right? Because our values of the variable, again, go on the horizontal axis. And then so around where is the most frequent values of the data? Like the low 21s, right? Like 21, there's 4 of them, or 21 exactly, 21.2, 21.3, 21.4. But you get out to low 19s or 22, and there's no data. So there's a low frequency. Again, you get a shape, right? You get a shape. Remember talking about skew. Is this right skewed or left skewed? Right skewed or left skewed? It's right skewed because our median is going to be over back in here, but then all this data up here is going to pull the average, the mean, this way a little bit. So it's skewed to the right because the center is more here at the high point, like the median. Mean is going to be further to the right. And then what about this? Left or right? That's left skewed, right? That's left skewed. Our median is going to be around 21 or high 20s, but then this data down here pulls that mean to the left. Okay, same thing with these DVDs. Probably wouldn't make sense to draw a curve for this one, but it's the same idea. We're seeing frequency vertically, and then the value of the variable horizontally. And so you get a shape. So this is kind of has many modes here. We got a mode around $200, a mode around 210, a mode around 220. Okay? So then we get these different shapes. So when you see something like this, you have to know what it means, right? You have to know what it means. What is it showing? So you think about what's being shown. It's a graph, so we need to know what the two quantities are, horizontal and vertical. So again, what's the horizontal going this way? What does that represent horizontally in these graphs? What's that? Value of the variable, right? So whatever the variable is, it's going to take on different values, and we're going to consider all the different values across here, and then the height of the curve means what? So when you see this J-shaped one here, this J-shaped, okay, what does it mean that the curve is real close to the axis here, and then it's farther away over here? So if we're working with these curves, we gotta understand what's going on. So, what do you think, Michael? What does it mean that the curve is up higher here and lower down here? Yeah. So when that variable takes on a higher value, we see more of that occurring, right? We see that at a higher frequency. When the lower that the value of the variable goes, we see that less and less frequent, less likely. Okay. All right. So the chapter 6 is about, you've heard of the bell-shaped curve, the normal distribution. That's what chapter 6 is about. That very first one there, bell-shaped. Okay. So what does that tell us about? What comment can you make about the frequency of the data? Frequency of the data in a bell-shaped curve. It's symmetric, okay. You say anything more? Whitney?
A higher frequency, the data occurs most often in the center.
Right. So in the center, and what do we call that? What's the?
The mean occurs around the median.
Okay, the mean and the median. The mean and the median of all our data, the middle of the data, is going to be the most frequent, right? So, or around the mean and the median is where we're going to get most of the data. Okay, highest frequency. The further away you get from the mean and the median, the less frequent or the less likely those values of the variable to show up, right? So that's what this curve means. You've got to think about it that way. Okay, so here was the heights of, I think it's college women. Okay, and so this was the relative frequency chart. And they broke the heights into classes of 1 inch at a time. Okay, so 60 to 61, 61 to 62, and we see that the relative frequency table here. And so then these bars, the bars then show the frequencies in these different classes. And so then what I want to point out is if you look at this particular region right here from 67 to 68, in the sample that they took, it was 240 women. And that had a relative frequency of 0.0735, which is what? 7.35% of the data fell in this area. So the relative frequency right here on the y-axis was 0.735 for this range, 67 to 68. But so notice something, that this shaded region, as a rectangle, right? What's the width of the rectangle? 1, right? And what's the height of the rectangle? What's the height of that rectangle?
0.0.
Yeah, so exactly. The relative frequency, 0.0735 is the height. So what would the area of that rectangle be? 1 times 0.0735. Or base times height, right? So the area, it's kind of, as you see that it's kind of like the area beneath the curve, within a range is matching up with the relative frequency or the probability of being in that range, because you could calculate the area of that rectangle. And there's a little part sticking over there, but it's pretty dang close to being the area of that rectangle, that shaded region. So we can think of areas under this curve as generating these relative frequencies. So it's like a visual version of relative frequency. Okay, so when we're doing these areas under the curve, this is where it comes from, right? It comes from this idea. So let's look at an example of this. So same thing, it says the area under the standard normal curve with parameters, the mean is 64.4, standard deviation 2.4, that lies to the left of 61 is 0.0783. So first of all, what does this mean? To the left of 61. What does that mean in terms of the female college students? To the left of 61. Hold on. In terms of the college students that were surveyed here, what do we mean when we say to the left of 61? Jason, what's that? Shorter than 61 inches, right? To the left, so on our scale, our variable is height. So on the left on the scale would be shorter than 61 inches, right? So that's what we mean by to the left. The left is values of the variable less than. To the right is values of the variable greater than, okay? So they're saying that with this distribution, to the left of 61 is 0.783, or this use this information to estimate the percentage of female students who are shorter than 61 inches. So we're going to use this information. If this area, they're saying that the area under the curve to the left of 61, so what I'm filling in red, the area is 0.0783. Okay? It says use this information to estimate the percentage of students who are shorter than 61 inches. Yeah? 7.83%. What do you think? Yeah, that's what we just said, that the area under the curve between certain values of the variable is the relative frequency that the data is in that range. Remember, because we took 1 times that other one, 0.0735, and that's the area of that rectangle. So area corresponds to relative frequency or probability. So this is 7.83%. If the area is 0.0783, then 7.83% of the women are less than 61 inches. Okay, so now let's use the table to obtain the exact percentage of female students who are shorter than 61 inches. So you do that, okay? So now use the table. You've done this before. So we want to know the percentage of female students who are shorter than 61. Go, you do that. Okay, and Ashlyn, tell me how you're doing that. What are you doing to calculate that? Which ones? Okay. So this one? This one? Tell me when to stop. This one? This one? This one? This one? Okay. So you said you added these together. Okay. And what exactly did you get? 0.0784. Okay, so obviously it's very, very close. Why isn't it exactly the same? So this is our hypothesis that area under the curve is relative frequency. Area under the curve for a certain region of, or certain interval of the variable gives us the same as the relative frequency for that interval of the variable. Why aren't they exactly the same?
Because there are some parts of the out of the curve.
Okay, so the actual, okay, so what you're saying is the actual rectangles reflect this, and so there's actually, the rectangles are going to be a little bit bigger. The area of the rectangles is going to be a little bit bigger than the actual red area that I drew, so that would show that agrees with that. That adding up the areas of those rectangles will be a larger number than the red area under the curve. Okay. Any questions on that? Does it make sense? So this is our big conclusion here. Area under the curve, same as relative frequency for that interval of the values of the variable. Okay, so we have, here's 3 different distributions here. And so I'm just going to draw some areas here. Let's do this. Okay, and then that. And then so these 3 areas that I've just sketched here, okay, what do each of those represent? So be specific. What do those areas, the values of those areas, mean? So how about, let's see, Henry, this first one. So I've drawn this area here on this green normal curve. What does that area represent? Yeah, okay, so so this isn't really a between situation. Yeah, you got it. So it's the relative frequency, but this is just kind of implying that it's going to be everything over here. So how can you kind of alter your answer a little bit? It's not really a between situation. Yeah, so I haven't told you. I haven't told you what the variable is. So there's some variable here that has some kind of range from like -6 up to 2 or something like that. But so you were almost perfect. It's just you wouldn't refer to this as a between situation. So how could you just adjust that part of it? What you said was perfect. But we're not talking, this isn't really talking about between two values. Instead, it's what? What's that? Equal. What's equal? So we got to know, when you see an area like this, we say, what is this area? What does this area represent? Really crucial that you can articulate this. Tell me your name again? Mac.
All the values less than -1.
All the values less than -1. What do we think? Is that? It has to do with all the values less than -1, but that area doesn't represent all the values less than. It has to do with that. Yeah.
Relative frequency left of -1.
Okay. Yeah. So it's the relative frequency of when the value of the variable is less than -1 for all the data where the variable is less than -1. So it's the relative frequency or probability. That the data that a randomly selected item from the population has a value less than -1, whatever that area is. Okay, so then what about this one? Here we go. This one right here. What does that area represent? Not between. Not between. So yeah, greater than 4. Greater than 4. So probability, that area, that is the probability or the relative frequency that the value of the variable greater than 4. Okay, what about this last one? Ninos. Okay, is it frequency? Remember this, that's something different. The value of the variable, right? So remember that frequency and relative frequency are two different things. Frequency is actually like counting how many. And relative frequency then is our chunk or a portion of 1. And that area will be a relative frequency. The area will be a relative frequency. And so in this case, it's the relative frequency or probability that the value of the variable is between 8 and 12. That's what that area represents. Okay. So I got some work for you guys. So I want you to answer the questions, but also try to draw the situation that they're giving you. And so to do that, you got to remember how the so you're kind of estimating. You're estimating where on the curve what's going on. You're going to try to make a sketch of this based on the percentage that they're giving you. Okay? So give this a shot. I'm going to hand back your quizzes from last week. Okay? If you want to work together, you're welcome to do that. Check your answers with each other. Where's Sabrina? If you want to glance at your score, that's fine, but try to stay focused on the task at hand and then look at this later. Yes. Kelly Leavitt. Levitt? Lee? Kelly Lee? Good. Taking notes? James. Kelly Neal. Eduardo. Selena. So you're answering the question that they ask, and then you're also representing it visually. That's your two tasks for each. Danny. Okay. So the question is, if the area to the left of 10 is 0.654, what percentage of all possible observations are less than 10? Selena, what do you think?
0.654.
0. So what percentage?
6.5.
That's 6.54%? No. How do you get percent? Multiply by 10?
Oh, sorry.
60.
65.
Yeah. Okay, so now the question is, let's see, and then so what about, and where'd you get, how'd you get that?
1 minus 0.654 or 100 minus 65.
Right, perfect. So if 65.4% of the observations are less than 10, then the rest have to be at least 10, right? The rest, you take 1, she said 1 minus 0.654 or 100 minus 65.4. And you got 34.6? Okay, so now the question is, if we were to draw this situation, where would 10 be on the variable scale, the value of 10? Would it be at A, B, C, D, or E, or maybe between two of those letters, between A and B, etc.? So where would you guess that in order to construct this visual image, we need to kind of figure out where 10 would be on the scale for the variable? Where do you think?
Between C and D.
He wants between C and D. We need 65% of the data to be less than 10. So, and lots of people agree. So yeah, somewhere over here, like this. At C would be 50%, right? Half the data would be below, so we need a little bit more. A little more than half. So this is that image that we want to draw for, and so right there is our 10. Or somewhere close to there. We're just estimating. If 65% of the data is less than 10, that 10 has got to be a little bit to the right of the middle. So we take more than half of the data, a little bit more than half of the data in our area. So now that I've done that first example, I'll give you a minute or two more. See if you can not only answer the questions, but create a good representation the way I did there by finding where the 10, about the 10 would be. Okay, and then check your answer with someone else. Answers. Okay. All right, Felipe, what do you think? This one, area under the density curve that lies to the right of 15 is 0.324. What percentage of all possible observations exceed 15? He wants 32.4%. Yeah, so lying to the right on the variable scale would be greater than. So if we want that the observations to be greater than 15, we know that's the same as the area, 32.4%. At most 15. Scott, did you get it? 67.6. And so if I put that same scale, A, B, C, D, E, on here, where would you say? In between or at which letter? For this one, 15. Where does 15 go along this if I were to put the same A, B, C, D letter scale? Where would you think? Around B. She wants around B. Agree with that, Scott? So 15 should be right here. Because then exceeding 15 would be 32.4%. Agree with that? Ashley, what do you think?
I'm pretty like almost in the same place for the 10 goals.
A little bit further to the right or left? So around D maybe?
Like still in between C.
Okay. All right, she's being precise there, yeah. Yeah, it's going to be here, right? So 15 is going to be like here. Why? Because we want about 1/3 of the observations to be greater than, not less than, greater than 15, exceed, right? And so then 2/3 would be something like this. So 15, we guess, would be about right there. Okay? The area under the density curve is between 30 and 40 is 0.832. What percentages of all possible observations are either less than 30 or greater than 40? See, Trevor, did you get this one? So the area between 30 and 40 is 0.832. What's the percentage of all possible observations less than 30 or greater than 40? Whitney?
16.8.
So why 16.8?
Because if I was on outside of that, was at 83.2%, so the outside of that would equal 16.8% if you subtract it from one.
Yeah, they gave you an area and then they asked you about all the rest of the area, didn't they? Right? So they gave you an area and then they said, we want the frequency or the relative frequency of not that. Less than 30, greater than 40. So you're going to take 1 minus, and you said that was 16 point.
16 or 20.68.
68. Okay, so where are 30 and 40 on this scale? Where are 30 and 40? Kayla, where would 30 and 40 be?
I marked it at like
B and D for 30 and 40. So let's give that a shot here. So like around here and around here. So is that about 83% of the area underneath the curve? Doesn't have to be perfect, but it's the right idea, right? Yeah, good. Maybe even further out over here. Further over here. It's almost 9/10 of the data, right? Something like that. Okay, so we'll just skip down to 19. So if one normal distribution has a mean of -4 and standard deviation of 3, the other has a mean of 6 and a standard deviation of 3. Do they have the same shape or are they centered at the same place? Question?
I have a question on 6.8.
Yeah.
Because we don't have, isn't it nearly impossible to tell which side of the 30 or 40 the majority of the 16.8 lies? So it'd be hard to plot that.
But it's or, so we're saying that it's really about what lies between 30 and 40, right? So between 30 and 40 is 0.832. That's like 80% of the data. So there would be no way, you couldn't put the 30 and 40 both on one side, because if you're both on one side, it'll have to be less than 50%. Right? Because from C to the right of C is what percent of the data? Where I've marked C. To the right of C is how much? 50. And to the left of C is? Okay, so if 30 and 40 doesn't lie on either side, if they're both on one side or both on this side, it's going to be less than 50%, right? So if it's 83%, then we know they've got to be straddling the middle to get 83% of the data. Does something like that. So it could, we don't know exactly where. It doesn't have to be centered. It might be,
Okay, that's fine.
yeah, it could be like this, you know. So we don't really know. That's possible too.
Okay.
Yeah, something like that. But because each side is 50%, we've got 83%, they have to be on either side. Yeah. Okay, so do these distributions have the same center or the same shape? Or both, or neither? So remember, the mean is like center, it's going to be the center of the normal distribution. So those are different. Okay, the ones that weigh it down at -4 weighs up at 6. But their shape is going to be the same because they have the same standard deviation. So if you look, bell curves have different shapes. So go back to this one. So what do you notice about the standard deviation of the red one compared to the green and the tan one? It's really pointy, and so where does that come from? The standard deviation is? Compared to the others? Bigger? Smaller. When you have a smaller standard deviation, you got to get all your data in a smaller range. So it needs to be high. It's going to be taller, right? Because these remember, the height is your relative frequency, and if you have a smaller standard deviation, you got to get more of your data around the middle, so that it's going to be taller. If you have a bigger standard deviation, the data is more spread out. So your data is spread out further, and so all the frequencies will be lower. So you get a lower, flatter curve. So these are all bell curves, but the standard deviation then governs what the actual shape of it will be. Okay, so remember in the two chapters ago, we did this standardized versions, the z-scores. And for a given mean and standard deviation, we could set up the z-score. So like, remember the mean and standard deviation, the mean is 9, the standard deviation is 2. Then to get the z-score, it'd be x minus 9 divided by 2. And that would normalize or standardize this curve into the z curve. Okay? And so that could be done for all of these. You'd have x minus 3 over 1/2, x minus -2 over 1. And when you do that, you get the standard normal curve. On the standard normal curve, what are the values on the x-axis? Super important question. We talked about this. So now, when you standardize a curve and get the z normal curve, what are those values? What do they represent on the x-axis, Daniel?
The mean becomes 0 and the standard deviation becomes 1.
Okay, and so what really are these numbers then? What are those values on the x-axis? Kesman, what are you going to say?
How far away the mean is from standard deviation?
I think you wanted it the other way around. How many standard deviations you are away from the mean? What were you going to say, Eduardo? Yeah, these are standard deviations. So the mean is 0, and then what this means is these values are a number of standard deviations. A number of standard deviations. This 2 is what? 2 standard deviations to the right of the mean. And so that's universal to all distributions. Somewhere in all normal distributions, there's some value of the variable that's 2 standard deviations to the right of the mean. If you find the z-score for that value of the variable, you're going to get 2. You're going to get 2. Super important. So these are standard deviations. Positive means to the right of the mean, negative means to the left. So the standardized then is the universal curve that represents all curves. We can find the z-score from any distribution, and it makes it standard so that it's always like this. And like we saw on the quiz, it gives you a way to compare scores from different distributions by comparing the z-score. So following along with that, the areas work out. Okay, so if say this is, so where's 2 standard deviations above the mean? What value of the variable here is 2 standard deviations above the mean? 13, because 9 is the mean, so there's 1 standard deviation will be 11, 2 will be 13, okay? And then what about for this one? What's 2 standard deviations above the mean here? It's not 1, it's half. Okay, and what about this one? 2 standard deviations above the mean here. 0, okay? So all these have a z-score of 2, but here's the thing, now that we're starting to talk about area. So therefore, these areas are equal as well. The same percentage of observations will be above 13 in this distribution, above 4 in this distribution, above 0 in this distribution, because it would be the percent of observations greater than 2 standard deviations above the mean. So those areas are equal. Those areas are equal. So just like we can compare z-scores, we can compare areas. So that's what this shows. So for any given normal curve with standard mean of mu, standard deviation sigma, if you find the... Oh, so then I didn't do it for the... Shoot. For this one as well. So and then the whole point is all 3 of those areas were equal and equal to this area. That's the point. So all 3 of those areas are equal. And equal to, under the standard normal curve, the area under the curve greater than 2. All those areas are equal. And so that's what this shows. The area on the curve that you're given for the normal curve between 2 values of the variable will be the same as the area under the standard normal curve for those corresponding z-scores. Same area. Okay, go. So this is the weights of adult green sea urchins are normally distributed with a mean of 52, standard deviation of 17.2. So this is the X for part A, and this is Z for part C. So for part A, what you're doing is you're putting some values. You're estimating where the values would go on this axis. So this Kelly over here, how did that go? Were you able to make some progress on that? Yep. Okay, so tell me what to put where. Right in the middle. Okay. 69 point. Okay. Okay, so here's a trick. You see where the curve is like the most curved here? See it's kind of flat here and then flat here? Look for the spot where it's kind of the most curved. See, that's about right there. Do you see that? That's 2 standard deviations above the mean. So that's a way you can do that. So you see it's kind of flat, and then it's curved, and here kind of somewhere around here it has the highest curve, and then it's flat again. So that right where it's bending the most. It's harder to see on these low flat ones. It's easier to see. See on the Z curve, it's like right there. Can you kind of see that? That's pretty close to 2. So what'd you say 2 was, Kelly? 86.4. And then this way? 34.8 and okay, and then it says the standardized version Z of X. So who got that? Z equals, Shelley, did you get that? How do we find Z given some value of X? Right? So if you had X, how would you calculate the Z score? Don't remember? Sabrina. That was right from the quiz. It's number 1 on the quiz, right? How do you get the Z score from the X? Scott, did you get it? Yep. X minus 52 divided by 17.2. Okay, so then that would be our Z distribution, and the mean would be, for Z, 0. And then again, look for where it's curved the most, right about there. It's 2, halfway between, 1, -2, -1. Okay? And then it says the percentage of adult green sea urchins with weights between 50 and 60 is equal to the area under the standard normal curve between what and what. So we're talking about, let's see, 50 and 60. So here's 50 and 60, something like that. Okay, so what we want to know is what Z values would give us the boundaries of the same area. So this is 50 and 60. So what are the Z values on either side of this region? So who got it? Yeah, Ninos. And how'd you get that? Right, so you're going to put the 50 in here to get the corresponding Z scored for X equals 50. Tell me what it was one more time. Okay. Is that what you got, Danielle? And then what'd you get for this one? You're going to put 60 in here. Okay, so the area between 50 and 60 on the normal curve for our distribution is the same as the area between -0.116 and 0.465 on the standard normal distribution. And what are these numbers again? What do they mean? Number of standard deviations. Number of standard deviations. That's what this is computing. How many standard deviations you are from the mean. Below is negative, above is positive. Okay? And so then whatever this area is the relative frequency of observations of these urchins in that from 50 to 60 grams. Okay, so now the question is, how do we get those areas? How do we get those areas? That's what we want to know. We want to know, okay, so that's great. That's the probability. That area is the probability. How do we get that area? So that's where this table comes in. That. Okay. Okay, so we want this probability of, we want to know what percentage, so we know that the percentage of adult free sea urchins with weights between 50 and 60, we know that that's going to be that area. The percentage of sea urchins is going to be that area. It's also going to be that area. But what is the area, right? We want to know what percentage is this? What percentage is this? That's where this chart comes in, okay? So this chart gives areas to the left of a certain z-score, always to the left, okay? These are always areas to the left of a certain z-score on the standard normal curve, okay? So if we just wanted to say less than 60, now we wanted to know the percentage less than 60. So that would be, say, all of this from here over, this whole area underneath here. You're going to go to this, and since that z-score is positive, you're going to look on the right chart. Notice, look up at the picture up above. Okay, you see that that's showing a z-score to the left of 0, to the right of 0, greater than 0, and you're going to get to the left. So what do we want? We want 0.465. So you're going to go down the column and look for 0.4, and that's right here. Oh, I can't draw on that. 0.4. For yours, it's the lowest row in the first kind of bank of rows. And then you're going to go to 0.465. Then you're going to go to 0.6 is here. 0.7 is here. Okay, so we're going to take, the best closest we can do is do the average of those two. Okay, so 0.46 is 0.6772, right? And 0.47 is 0.6808. So we want the average of those two, which would be 0.465. What do you get? So for z equals 0.465, we get an area of 0.679. Does everyone get that? Does that make sense? So, the relative frequency of urchins that are less than 60 grams is going to be the same as the area under the standard normal curve below 0.465, which we just found from the table to be 0.679 or 67.9%. But now we want between 50 and 60, so what do we have to do? We have to get rid of this part of it, that area. So what do? Negative 0.116. You're going to look on the left chart. You're going to do the same thing. You're going to go to negative 0.1. And that's all the way, almost all the way to the bottom. Second to last row, right? And we want between 0.11 and 1.2. So that's going to be between 0.4562 and 0.4522. Yours is over here. So on your chart, it's right down here in the lower right-hand corner. Okay. So 6, that's close enough to halfway between those. So what's halfway between 0.12 and 0.11? As soon as you get it, tell me. Did someone else get that? What does that mean? That means that 45% of sea urchins have a mass less than 50. It's to the left. So how are we going to get the percentage of urchins between 50 and 60 grams? You're going to subtract it, right? You're going to take that total area less than 60, which was 0.679, and subtract away the area that was less than negative 0.116. And that'll give you the area between. Does it make sense? So it's the total area left of here minus that leaves that. We're going to take 0.679 minus 0.454 equals, who's got it? 0.22, 22.5%, or close to 1/4 of the sea urchins have a mass between 50 and 60 grams, because that 0.225 is the area between the corresponding z-scores for 50 grams and 60 grams. Does it make sense? Okay, you've got plenty to get started on your homework for Sunday, and I posted the quiz will pop up at 9 a.m. today.